So we're going to, in this video, look at finding locations of horizontal and vertical tangency for a parametrically defined curve. So in this case, we want to find the locations of horizontal and vertical tangency for this parametrically defined curve. I graphed it in GeoGebra, and you can see that the graph of this curve is an ellipse. And the idea is that horizontal tangency will occur when the derivative of the relation is 0, and vertical tangency will occur when the derivative is undefined. If you think about taking a ratio a over b, if this is the derivative, then if you take the limit as b goes to 0, if the numerator is a constant, this ratio becomes infinite. So there's a sense in which you can say vertical tangent line has infinite slope. So what we'll do first is calculate the derivative. So we'll say, hey, dy dx. And dy dx is going to be d theta. We're parameterizing with respect to theta in this example. So d theta of the y, parameterized y. So d theta of -2 plus sine theta. And then we divide it by d theta of x of theta. But x of theta is just 5 plus 3 cosine theta. So d theta of 5 plus 3 times the cosine of theta. So the derivative of the numerator in this case is just going to be the cosine of theta over the derivative of the denominator is going to be -3 times the sine of theta. So horizontal tangency will happen when the derivative is equal to 0, and the derivative can only be equal to 0 if the numerator is 0. And the vertical tangencies will occur when the denominator of the derivative is equal to 0, or we get an undefined denominator, which means the slope is becoming infinitely large. So to find the horizontal points of tangency, can't even spell, horizontal tangency, we're going to take the cosine of theta and set it equal to 0. And there's two ways we could get at this. We could say, hey, this is going to correspond to a special angle, either theta equals pi over 2 or 3 pi over 2. That would be one way to get it. And we know that for either of these, we could add plus 2 pi k to either one of these angles, and we get infinitely many answers. Because this curve's been defined parametrically, we're just orbiting around this ellipse. Theta can can go to infinity, and you just continue to orbit. So one way to do it is to take advantage of special angles, and because we can see that we're only looking for 2 points of horizontal tangency, we don't have to worry about the fact that there's infinitely many solutions. We just pick 2 and we get the points that we need. The other way that we could do this is we could think of this as being a trigonometric function where we want to solve it a little bit more rigorously. So one thing that we could do is say, hey, we'll take the arc cosine of both sides. And we'll take the arc cosine of 0, and when we take the arc cosine of both sides, because of the even symmetry of the cosine function, you get 2 possible answers. You get a plus or a minus, and it's plus 2 pi k because those repeat over and over again. And then you say, hey, when is the cosine equal to 0? Well, the arc whose cosine is 0 is pi over 2, so we get plus or minus pi over 2 plus 2 pi k. In this particular case, because we're only hunting for 2 points, we're not really caring about the plus 2 pi k, but I can use the plus or minus pi over 2 just as easily as I could use pi over 2, 3 pi over 2 to generate my points. So my points of tangency now will come from just plugging in pi over 2 and negative pi over 2 into the parameterized equation. So for example, if we did x evaluated at pi over 2, we're going to get 5 plus 3 times the cosine of pi over 2. But the cosine of pi over 2 is 0, so we're just going to get 5. And the y coordinate that's going to go with that would be y of pi over 2, which would equal, from here, -2 plus the sine of pi over 2. And the sine of pi over 2 is equal to 1. So we get negative 2 plus 1 is just negative 1. So you can see that we've got a location at the ordered pair. X is 5, y is negative 1. And that's corresponding to this point right here, 5 comma negative 1. So to get this other point, I could just plug the negative pi over 2 into the same two functions. We could say, hey, when x is when theta is negative pi over 2, what is x? But that's just going to be 5 plus 3 times the cosine of negative pi over 2, which is still just going to be 5 because the cosine of negative pi over 2 is still going to be 0. And when we do y evaluated at negative pi over 2, we get that this is going to be negative 2 plus the sine of negative pi over 2. But the sine of negative pi over 2 is negative 1, so we get negative 2 minus 1, which is just equal to negative 3, and that gives us our other location. X is 5, and y is negative 3. So those were the points of horizontal tangency. So if we want now to find the points of vertical tangency, we need to determine when dy dx is undefined, and dy dx is going to be undefined when the denominator is equal to 0. The only thing we need to be careful for when we're doing a problem like this is we need to remember that if we get the indeterminate form 0 over 0, instead of getting a horizontal or vertical tangent line, that's when we get those sharp cusp in the graph. So yes, the horizontal tangency will occur when the numerator is 0, but the denominator can't be 0 at the same time. Similarly, we get the vertical tangent lines when the denominator of the derivative is equal to 0, but the numerator can't be 0 at the same time. So in this case, I don't need to worry about it because of the functions that I have. I can see that I'm going to get very different values for theta, generating the 0 in the numerator and the denominator. So the vertical tangency is going to happen when we get negative 3 times the sine of theta equaling 0, which just means the sine of theta needs to equal 0. And again, this is a special angle situation, so we could just look at this and identify to get the 2 points that we need. We really only need 2 points on the interval from 0 to 2 pi. We could pick sine of theta will be 0 at 0 and pi on the unit circle and not worry about the fact that there's infinitely many solutions. We could walk through it the way that we did here, but again, because we're in a special angle situation, we don't need to. And then to find the locations, we do the same thing that we just did. We plug those values in. So if we're working with theta equal to 0, that's what is x going to be? X of 0 is going to be 5 plus 3 times the cosine of 0 is going to be 5 plus 3 is 8 because the cosine of 0 is 1. So we'll get that location out here at 8 comma. To get the other point, we plug the 0 in for y. So we get y of 0 equals negative 2 plus the sine of 0. And this is just going to be negative 2 because the sine of 0 is 0. So we get 8 and negative 2. And to get the other point, we just plug in our pi. So we get x of pi equals 5 plus 3 times the cosine of pi equals 5 minus 3 because the cosine of pi is negative 1. So we'll get a minus, and that'll give us the 2. So the location is at 2. And finally, plug pi into parameterized y. We get negative 2 plus the sine of pi, and the sine of pi is 0, so we just get the negative 2. So that's how we find the locations of horizontal and vertical tangency for parametrically defined curves.